Alright guys, in class today we worked on titration problems and kind of looking at how they work and what they do. What I want to do is spend a little bit more time breaking down the math and what's going on in that math, or why we're doing that math for the different pieces of a titration. In a titration, you typically have four main things that you're going to calculate. For the most part, you have an initial pH. You typically have a midpoint pH, but sometimes it's not always a midpoint. Sometimes it's just a random point sometime between initial and equivalence point. You have the equivalence point, and you typically have some point after the equivalence point, at least when you're doing a titration curve. Now, you're not always going to do all four of those in one problem, but those are the common four parts or pieces that would be asked. So what I want to do for the next video or so is just go through those different math problems and just kind of talk about how they work and what we're doing and why they work that way. And then I'm probably going to break down the problem you got from homework as well, the homework from today, break that down and kind of work through that problem with you. So first and foremost, we have an acid, which is acetic acid, and we have sodium hydroxide, which is a base. Your acetic acid, if you remember, is a weak acid. Hopefully we are working on remembering who our strong acids are and our strong bases are. So acetic acid is a weak acid. We're going to start with a 1 molar solution of it, and we're going to measure out 25 milliliters of that 1 molar solution. That's going to go into a flask that's going to sit underneath the burette, if you remember how to do a titration lab from last semester. We're then going to take sodium hydroxide, fill the burette with the sodium hydroxide, and we're going to be adding this 1 molar solution of sodium hydroxide to the 1 molar solution of acetic acid to titrate it, to figure out different aspects of it. In most cases, what you would be trying to do is figure out the molarity of the solution in the flask. We're just not going to work it from that direction right now. We're going to work it from just seeing the math and how the math works in each individual part. So let's say we're talking about the initial pH of the solution. Well, this is where you have to ask yourself, well, who's in the solution? Well, initially, all we have is acetic acid. So, again, you have to ask yourself, okay, what is acetic acid? Well, acetic acid is a weak acid. So, what does that mean? What that means is, what we've been doing all the way along, is that acetic acid is going to dissociate only a little bit, and it's going to dissociate into hydronium ions and acetate ions. So again, like we talked about in class, this is nothing new. This is a weak acid problem that we've been doing all the way along. So, and we need another piece of information, sorry about that. We would be told Ka is 1.8 times 10 to the negative fifth, and that would be up there. Okay, so to solve this problem, we solve it like we always do. If we're trying to find pH, remember pH equals the negative log the hydrogen, our hydronium ion concentration. So what we're looking for is the hydrogen ion concentration, which is this guy right here. Unlike a strong acid, we cannot assume all of this breaks down because it doesn't. By definition, it's weak. So we have to use our ICE table to determine how much does break down. So we have our acid, we're told, is 1 molar. We don't care about water because it's a liquid. And we assume 0 of our products, because again, this is just the initial before any reaction or anything has occurred. So minus x, plus x, plus x, and 1.0 minus x, x and x. Now from there, we would solve it using our equilibrium expression, which of course is our products over our reactants, just like it always has been. So K is 1.8 times 10 to the negative fifth. That's going to equal products, which are x over our reactants. Okay, so to solve this, we would multiply by 1.0. And remember, that's not always 1 down there. That's just what our molarity is initially. And then we're going to square root because we have x times x, which would give us x squared. So what we end up with is x is equal to 4.24. And actually, since we're doing 2 sig figs, we'll do 4.2 times 10 to the negative 3 molar. Now, again, recognizing that we're trying to find pH, so we're trying to find the concentration of hydrogen. Well, X is the concentration of hydrogen. So all we have to do from here is take the negative log of the concentration we just calculated, so 4.2 times 10 to the negative 3. And we're expecting something around the 2, 3 range because look at our exponent. Okay, and what we actually get is that our pH for our initial solution of just the acetic acid is 2.37. So that's how we would work through a titration, the initial part of a titration, as we would just look at who we have initially. In this case, we have a weak acid, so we treat it like a weak acid. If we had a weak base, we would treat it like a weak base. If we had a strong acid or strong base, we would treat it like a strong acid, strong base. So again, the thing with titration reactions is recognizing what's going on and then how does that affect who's in the solution. So at this point in time, we haven't added anything except acetic acid to water. So therefore, the only things in solution are acetic acid and water. And then we work through how it behaves, solve the ice table for our hydrogen ion concentration, plug that into our pH equation, and solve for our pH. Okay, so let's look at it from the next step, which a lot of times can be a midpoint step, if you will. So let's get rid of all that. Okay, and we're going to keep with the same acid and base that we're doing because all we're now going to start doing is adding the sodium hydroxide to the acetic acid. So kind of imagine in your head you're now opening up the burette and letting some of the sodium hydroxide fall into the acetic acid. And let's say we add 10 milliliters of the NaOH solution up here. So we're adding 10 milliliters of this guy. Okay, and we're going to call this not really a midpoint, because midpoint is when you do have half moles of sodium hydroxide as you do the acid, but kind of maybe an in-between pH. So this is in between the initial where we started, where it's just the pure acid, and going to the equivalence point. So at this point in time, what we have to recognize is that there is a reaction occurring. We have sodium hydroxide reacting with acetic acid, which means we don't just have pure acetic acid floating in solution anymore. We have a reaction. So the first thing we need to do is write that reaction. So we end up with the acetic acid. Okay. And you can either write the sodium hydroxide as NaOH or you can write it as OH, because think net ionic, a weak acid would not be broken down. By definition, it doesn't dissociate completely, whereas a strong base would be broken down. So you can kind of do it either way, whatever you're more comfortable with. So we end up with the sodium acetate or the acetate ion. Okay, sorry about that. Okay, and we end up with water. So again, note that this is an actual reaction. And the way you would write that, again, if you want to just write it without the sodium present, just maybe so it doesn't confuse you, is you just drop the sodium. And again, if you remember, the reason why we're dropping the sodium is because we're writing a net ionic reaction, meaning we're not showing the spectator ions. Either way is acceptable. It's kind of up to you. I will typically do the second way over the first way. So kind of pick and choose which one you want. And again, College Board is typically going to do it the second way too, because that is the chemist way of writing it, is with a net ionic equation. So we have this reaction. And again, we have to recognize that it's a reaction, and because it is a reaction, notice our arrow, it's going to completion. So from here, what we have to ask ourselves is, okay, what's in solution with this reaction, or what's going to happen after the reaction? And the way we do that is we're going to do stoichiometry. Okay, and we do stoichiometry with calculating mole value. And if you remember, molarity equals moles over liters. So if we're trying to calculate moles, moles is going to equal molarity times liters. So what we can do is take our molarities and multiply it by our liter values. Please remember, these are typically in milliliters. And if you're watching any of the other videos like Bozeman or Nimsey, a lot of times they'll do something called millimoles, meaning they leave it in milliliters and they get millimoles. It's not something I typically do, but you're more than welcome to do that as well. It does keep your numbers a little bit cleaner. But I'm going to go ahead and convert this to liters. So we have 0.025 liters multiplied by 1 molar, and we get 0.025 moles of acetic acid. Then we have our sodium hydroxide. We have 10 milliliters of a 1 molar solution. Well, this is 0.010 liters, so times 1 gives you 0.010 moles. And again, we would have 0 and 0 of these to begin with. Okay, and again, we are looking at moles here, so that plays a big role when we go back and calculate our pH. So from here, we recognize it's a stoichiometry problem. We're given 2 starting values. Notice here, this is the smallest, so it is the one we're going to subtract. Okay, our add onto this side. And of course, we really don't care about water, just like we never do. So from here, what we're left with is 0.015 moles, 0 moles of hydroxide, and 0.010 moles of the acetate ion. Okay, so from here, what we can do is recognize that with the hydroxide being gone, he's all used up, the only species we have left in solution are the acetate, or the acetic acid, and the acetate ion. And so if we remember back, we're basically now going back to the original equilibrium that occurred due to acetic acid. Meaning, I'm going to scroll down a little bit, oops, sorry, and we have our original reaction, which is the acetic acid plus water forming hydronium and acetate ions. And again, if we're going to do an ice table to determine pH, again, concentration of hydronium, we need to have concentration to go in here, not mole value. Okay, so to get molarity, remember it's moles over liters. We have our mole value, so we're going to divide that by liters. But we can't forget that we started with 25 milliliters, and we added 10 milliliters to it, which means we actually have 35 milliliters total. So that means we are now going to be dividing these guys by 0.035 liters. And then we're going to put them in their respective place down in our ice table. So we end up with 0.42, we'll call it 0.43 if we're going to deal with 2 sig figs, and again, this is molarity. And we end up with 0.29 over here. And again, notice what we have here is a buffer solution that we just created due to the fact that the reaction with sodium hydroxide is producing a little bit of the salt. Okay? And we solve this just like we always solve it. We assume 0 for our hydronium, which means we're shifting in that direction. Okay, and we now solve this using our K expression. So 1.8 times 10 to the negative 5th. And remember, K is not changing because our reaction is not changing. It's the same reaction we used in our first ice table. Okay, products over reactants, so X times 0.29. And remember, we're getting rid of the minus X and plus X because we are assuming due to the size of K that X is negligible. Okay, and what we get from here is that X equals 2.7 times 10 to the negative 5th. And again, notice that that is our hydrogen ion concentration. So all we have to do from here is take the negative log of it to get pH. So negative log of 2.7 times 10 to the negative 5th. And again, if we look at our exponent, we're expecting something around the 4 range, 5 to 4, or really between 5 and 4. So what we actually get when we calculate this is our pH at this in-between point, not really a midpoint, but in-between point, is going to be 4.57. Okay, so that is the first 2 points that we have in a titration that a lot of times we're asked to calculate. We have initial point, which was just looking at the original acid and its equilibrium. If it was a strong acid, it would be a lot easier, but it's a weak acid, so we use the equilibrium ice table. And a midpoint, meaning after we've added some of the hydroxide, which means we do stoichiometry, figure out what's left over. What's left over is part of the equilibrium, so we plug that back into the original equilibrium reaction, and we solve it out. All right, thanks, guys. I'll come back in just a minute, and we will do the next 2 steps, which is going to be the equivalence point and the Hasse equivalence point. Thanks. Bye.